Okay, hello everyone. In this video, we're going to be talking a bit about organic molecules. So these are often called the molecules of life. And in this set of slides for part one here, we're going to discuss what makes carbon so unique and so versatile and can make complex enough molecules for life. We're going to identify how you react with organic compounds in your everyday life. We're going to talk about a few different places where you may not have realized you interact with them. And we're going to distinguish some kinds of organic chemicals called alkanes, alkenes, alkynes, and aromatic hydrocarbons. After these slides into part two, we are going to actually talk about how to name those hydrocarbons. And then from there, we will talk about some of the reactions they participate in. And then we'll also talk about, in the end, some of the functional groups where we're talking about what kinds of things can be substituted onto organic molecules and how those kind of affect us in our lives as well. So if you've ever ridden in a motor vehicle, smelled perfumes, tasted sugar, you've experienced the magic of carbon and organic molecules. So let's get into it. The molecules of life. So this chapter is spending some time discussing organic chemistry. These molecules are very unique, and you'll see some of the things that, some of the ways that they bond and things like that, where they kind of are a little bit unique than some of the things we've looked at in the past because we focused on inorganic molecules. Now it's time to talk about the organic molecules. So they're really unique. They're critical to our world. They are often called the molecules of life because we are carbon-based life forms. Everything that you see that you would consider to be alive in life is a carbon-based life form. So we rely on these really, really unique properties of carbon to achieve life. Organic molecules are also responsible for most smells. Sugar is an organic molecule, and gasoline is full of organic molecules that power our car. So we couldn't go a day, a moment, even a split second without organic molecules because we wouldn't exist without them. So let's get into it. Let's talk a little bit about what they are. So, organic. That's kind of a way of growing vegetables and fruits, right? Well, yeah, okay, true, yeah. Here, when we're talking about organic fruits and vegetables, we're talking about fruits and vegetables that have been grown without pesticides and things like that. However, we use it one way in a kind of layman's everyday context. However, in chemistry, organic molecules are molecules that contain mainly carbon, combined with a few other elements like hydrogen, oxygen, nitrogen, and sulfur, for example. These elements form a versatile set of compounds, and they have very unique properties based upon their structures. So an interesting fun fact here is that for a long time, it was thought that organic molecules could actually not be synthesized because they contained the vital force. So like when you wanted to get sugar, you had to get it from sugarcane or beets or something like that because you could not go into a chemistry lab and make sugar. Because only living things could manufacture that. So these molecules that we called organic were molecules of life, and then inorganic molecules were those that we kind of basically could synthesize in labs. So that's kind of where the naming scheme comes from there. However, we know that this is not true due to the synthesis of urea. That might be ringing some bells for you guys if you know what I'm talking about, but we actually figured out that we could synthesize urine in the lab, basically, was what the first organic molecule we were able to synthesize is. So, like, organic chemistry was kick-started by pee, for lack of a better word. So, in that synthesis, it kind of has a not very noble origin of organic chemistry there. However, it is actually the basis for like modern pharmaceutical drugs and things like that, like it helped us to understand the molecules of life better. So a lot of the things we understand here in organic chemistry actually came from the fact that urine was the first thing we were able to synthesize, or at least the compound urea from urine, for example. So organic synthesis comes from an ignoble place, but it does some of the most noble things, keeping us alive and helping us to sustain life for far longer than we ever have in this field through some of the information we've learned about organic synthesis. So you might be wondering, why carbon? Why are we carbon-based life forms? Well, carbon can actually form some of the most complex structures in chemistry. So it can form more compounds. It can actually form more compounds than all of the rest of the elements on the periodic table combined. So like if you took all of the compounds that every other element on the periodic table could form, and you compared it to the amount of compounds that carbon can form, carbon wins. The complexity and the intricacy of these compounds is amazing and beautiful, and it's awesome. And so carbon can sustain such complex structures, and these are kind of the things that we believe led to life, that we could have these complex structure molecules. So why does it do this? Well, it has 4 valence electrons and therefore tends to form 4 bonds. So for our purposes in this class, carbon's always going to form 4 bonds. It takes really complex organic chemistry if carbon's not going to do that. So carbon's always going to form 4 bonds. So this is why it's able to complete those, create those complex structures with itself. So I've got a few just compounds we'll talk a bit more about on your screen here. So we can have like chained carbons where we just have a really, really long chain of carbons, like oils and fats and things like that, are these huge long chains of carbon, 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 carbon. We have things here like isobutane. So, for example, butane is a organic molecule. That's a fuel that we often use. And we can see that it can make these cool branched structures as well. And then two, we talked about this a little bit in the Lewis structures chapter. However, I got to take back a statement. Molecules can form rings. I know we talked about it a bit then when I said, nah, they can't form rings, don't worry about that. Actually, carbon is really unique in the fact that it can form rings, and it'll incorporate other elements into its rings as well. And a lot of these cyclic structures, these ring-like structures, are really, really cool and can do really great things in organic chemistry. So yes, we can make ring-like structures, however, they're just often carbon-containing. So with these intense complex structures, you can start to build these together as well. So you might have a really, really long carbon chain with a bunch of branches coming off of it, and maybe it'll have a cyclic group on there as well, like a group that makes like a circle, just like this cyclohexane does. So all of these come together to create those complex structures that we can't really form with any other kind of element. So carbon is really unique because it can create these awesome complex structures, and those complex structures can all be kind of combined to make even more complex structures. So it's really cool. It's really cool. So that being said, we kind of got to spend a little bit of time in this first set of slides here kind of establishing a basis for what we're talking about when we're talking about organic compounds. We're establishing the basis here. We'll talk about naming in the next set, and we'll talk about different structural properties and reactions as well. So here again, we're establishing a basis. So hydrocarbons are kind of what we're going to be talking about for most of our time, which are compounds that contain only carbon and hydrogen. Hence the name. Hydro, hydrogen, carbon, carbon, hydrocarbon, right? These are often used as fuels. We're going to be talking about lots of different ways we use hydrocarbons, but one way is as fuels because we can take a lot of energy from those carbon bonds. So remember, when you want to break a bond, you got to put in a little bit of spark of energy, then a lot of energy tends to come back out, especially when we're breaking these carbon-carbon bonds. So maybe like the spark of a lighter, and then fire can continue to burn beyond that, breaking the chemical bonds and releasing the energy contained within them. So it's pretty cool. They're a lot of our fuels and stuff. So we're going to talk about a few kinds of hydrocarbons to start with. Again, today we're just going to discuss them, and then next time we'll get into actually perfectly naming them. So we're going to talk about 3 different kinds of hydrocarbons, and then we'll talk about aromatic hydrocarbons, okay? So alkanes are one form of hydrocarbon that and what makes them unique is that they only contain single bonds. On your screen, and each time we talk about a different kind of hydrocarbon, I will give you the simplest version of that hydrocarbon. So the simplest version of a hydrocarbon, a compound that only contains carbon and only contains hydrogen, and only has single bonds, is going to be methane, here pictured on your screen. You can see that it's just single bonded to a bunch of hydrogens. And so when we have a hydrocarbon that only contains single bonds, we call this saturated. So we call this a saturated hydrocarbon. So I like to think of it saturated with all of the hydrocarbons it can hold. It's like, we've packed them all in. We have the maximum number. Just like when we were talking about in solutions chemistry, a saturated solution had that exact maximum of solute in solution. Well, here, it's the exact amount of hydrogens I could pack around all of my carbons so that my carbons each had 4 bonds, all single bonds, no double bonds, no triple bonds to be seen. So that's kind of what makes up an alkane. When we're naming alkanes, they're going to have that ANE ending. So if you hear something that ends in ANE, well, then that's going to be an alkane. So, for example here, again, we have methane. We can also talk about the chemical formula of how alkanes set themselves up. So that means that, here we have carbon to the N, hydrogen to the 2N plus 2. So basically what I'm saying is for every 1 carbon I have 2N plus 2 hydrogens in any case. So if you're breaking down a chemical formula and you can make the chemical formula fit this format, well then it's an alkane. So for example, here I have methane, which is C sub 1, H sub 4. So that's like C sub N equals 1. And then I can say that 2 times 1 plus 2 is 4. So it fits this pattern, C sub 1, H sub 4. So this is the proper chemical formula for methane, and we can compare this chemical formula to the standard kind of format here of an alkane and see that methane should be an alkane. Or CH4 should be an alkane, if you want to look at it that way. Here is the structural formula. They're calling it the structural formula. It's also the Lewis structure. We can kind of use that in these cases interchangeably. Sometimes it can be a little bit different, but for our purposes for right now, we can just say these are the Lewis structures. So you can see that our Lewis structure only contains single bonds. If that Lewis structure or that depiction of it only contains single bonds, hey, it's an alkane. And here's the space-filling model for your enjoyment. You can't really see the bonds in a space-filling model, so it's a bit tougher to see whether it's an alkene, or a alkyne, or something like that. So I'm not going to ask you to look at the space-filling model and determine whether it's an alkane, alkene, or alkyne. However, I do expect that you could look at the chemical formula and look at a structural formula and determine if you have an alkane, or to look at the name of something like methane, C-A-N-E at the end, and know that's an alkane. So let's look at some other alkanes over here. So here we have ethane, propane, and butane. So you may have heard of propane and butane before. Those are often fuels that we use, like a propane grill or a butane torch or something like that. There are propane torches as well. But you can see that each of these fit that formula where it's C to a certain number, H to the 2n plus 2 of that number, right? So here we have C sub 3, so we would have H to the 2 times 3 plus 2. 2 times 3 is 6, plus 2 is 8. Checks out. So propane, ANE, we can see that that would be an alkane by the name. We have the chemical formula that properly fits. And if I look at any of these structures, I see that they each individually have all single bonds within them. So if you're looking at this, or if you're looking at any of these individual pictures here, you should be able to identify the alkanes by the ANE ending, their chemical formula, or the fact that they all are just a bunch of carbons, a bunch of hydrogens, and they only have single bonds in that structure. So those are alkanes. Alkenes, so these kind of get a little complicated. You got to make sure you're saying alkane, alkene, or alkyne. We'll talk about those. And you have to make sure you're not swapping your vowels and you're spelling them correctly as well, because it can be quite tough in these cases to make sure you're saying what you're meaning. So you have to be extra careful because they all have very similar names. So alkenes are hydrocarbons that have at least one double bond. So here you can see the most simple alkene you could have. This is ethene or ethylene, you may have heard of before. So this is just an older naming scheme with ethylene. However, ethene is the name we will be using in class. So you can see down here that the simplest formula has to have 2 carbons to be able to show a double bond in there. So alkanes are a little unique where they can have a single carbon. However, alkenes, alkynes have to have at least 2 carbons in their most simplest format to be able to show at least a double bond, and we'll talk about the alkanes. So that being said, we call alkenes unsaturated. I like to think of it as it's unsaturated because you could break that double bond and shove more hydrogens in there. Like, this is not the maximum amount of hydrogens we could have around it. That would be ethane, where ethane has all of these hydrogens around it. So this is saturated. However, here with a double bond, that indicates that we have an unsaturated hydrocarbon. So now these saturated and unsaturated terms may also sound familiar to you as well, because we have saturated and unsaturated fats in our diet. So if we have unsaturated fats in our diet, that means they somewhere in their long hydrocarbon chain have a double bond or a triple bond or something like that, where we don't have that maximum number of hydrogens around it. However, when you're eating a saturated fat, it has all of those hydrogens around it. So it also, those saturated and unsaturated apply to some of the foods we eat too, because here hydrocarbons are fats and oils that we use to cook and eat as well. So here, again, this is unsaturated because realistically, I could break this double bond and stick another hydrogen on each of these. So they take the chemical formula C sub N 2 sub or H sub 2N. So for every 1 carbon you have twice as many hydrogens. So ethene here is C2H4. I can check that it matches that chemical formula of C to the 2, H to the 2 times 2, which is 4. So here again, you can see the space filling model. You can see that ethane space filling model is much more crowded up here versus that ethene space filling model. You can see that we're kind of missing some of those hydrogens that we might possibly have. So again, unsaturated. So let's look at some more alkenes. So here's a giant list of alkenes as well. So again, here we have ethene. That's the most simple one. Here we have propene with 3 carbons. So again, anytime you see that ene ending, you can assume it has a double bond somewhere in the structure and that it is an alkene. When you're looking at your chemical formula, you can see that all of these chemical formulas follow that same format of C sub 2 or C sub N, H sub 2N. And here we can see in these Lewis structures or structural formulas that we can see a double bond in each of these structures. Next time we'll talk about what these ones mean, but technically these double bonds could appear anywhere in our structure. They don't have to be at the end, they could be in the middle somewhere, and we'll talk about those cases next time. So here we're just giving examples. This is just what it looks like when you have a double bond present in those long hydrocarbon chains. The book also gives you the condensed structural formula, which I would just like to point out here, if I gave you a condensed structural formula, it should be pretty easy to see if there's double, single, or triple bonds in it, because we literally draw the bonds into this chemical formula. So what we're doing when we're writing these out are kind of grouping the carbons with the hydrogens around them rather than trying to condense the formula into something that looks like the molecular formula here, where we have it all shoved together. Here we're trying to spread it out. We'll show you where the double bond is, and we'll group those different groups of carbon and hydrogen together. So what I'm saying is this, is if you try to compare the structure here of butene to the condensed structural formula, what you see is you have CH2, well, there's CH2, there's the double bond, CH, CH, CH2, CH2, and we have a CH3 group here on the end. So that's what it's trying to tell you with the condensed structural formula. So if I gave you something like that as well, it should be pretty easy to see what kind of hydrocarbon you have there as well, denoting that like single bond, double bond, and we'll get to the triple bonds. So again, an alkene is going to have an ENE ending in the name. The molecular formula is going to follow the format of C sub N, H sub 2 times N, so you have twice the hydrogen for as many carbons as you have. We had 2. You should be able to look at the structural formula or that condensed structural formula as well to determine if this is an alkene, alkane, or alkyne. And an alkene has a double bond somewhere in its structure. So alkenes are ENE, C sub 2, H sub 2N, and have a double bond somewhere in their pictured structure. Can you guess what the alkynes are going to be? Alkynes are hydrocarbons that contain at least one triple bond. So we again call this unsaturated because again you could like break the triple bond and shove more hydrogens in there. This is not the maximum number of hydrogens you could have for 2 carbons. They tend to take the chemical formula C sub N, H sub 2N minus 2. So here, ethyne is ethyne would be C2H2. So we can see that it fits this chemical formula, C sub 2, H sub 2 times 2 minus 2, so 2 times 2 is 4, minus 2 is 2. So here, our chemical formula fits this format as well. And ethyne has that YNE ending. If you check out the structure, you can see that you have a triple bond right in the center between those 2 carbons. Again, when we're talking about alkenes and alkynes, it takes at least 2 carbons to make their like smallest structural formula because we have to be able to see that triple bond there. And here's the space filling bottle for your enjoyment. Alkynes, again, here's a gigantic list of them as well that you should be familiar with. So in each of them, I can see that YNE ending. And I can see that my molecular formulas fit this format up here. So if I checked out any of these, let's say C6H10, for example, you'd have C sub 6 and then H with sub 2 times 6 minus 2. So 2 times 6 is 12, minus 2 is 10. Boom, it fits our format. Nice. So if you're looking at the structural formula, again, you can pick out a triple bond somewhere in the structural formula. It could be anywhere in some of these longer structures, but we'll talk about that when we get to naming. But if you see a triple bond, it is an alkyne. And here are the structural or the condensed structural formulas as well. And we just can see that there is a triple bond represented by 3 lines there. So you should be able to check out any of these different formats and totally understand that you have an alkyne by the name ending in YNE, that molecular formula following the format of C sub N, H sub 2 minus N. And if you look at the structural formula, aka Lewis structure in this case, and the condensed structural formula written out like this, you can see that there is just a triple bond represented by 3 lines somewhere in your structure. So, alkanes, single bonds, alkenes, double bonds, alkynes, triple bonds. So alkenes, alkynes, and alkanes are going to be these kind of long structures, these chain-like carbons up together. However, we did mention that we do have these cyclic structures that hydrocarbons can form as well. So Kekulé was the first scientist to propose this idea of a molecule called benzene. You can see it over here on your screen. There's a carbon hiding back behind my head. I'm sorry, I can't make my video any smaller. But the idea here is that he was thinking of these long carbon chains, and I think this is really cool, as snakes. So he was thinking about them kind of snaking around. They don't really have a ton of flexibility in their chains, but he was thinking about them as snakes, and he thought, what happens if the snake runs around and grabs its tail and forms a circle? So you may have thought about this before or heard of an Ouroboros. So I have one pictured here, the snake biting its tail in perpetuity. So this was his inspiration for thinking of the cyclic structures of hydrocarbons that we now call aromatic hydrocarbons, and this molecule here called benzene that we'll talk a little bit more about in just a second because it's quite interesting. So that being said, these aromatic carbons are ring-like carbon structures. So if it forms a ring, we're going to call it an aromatic carbon structure. These are the ones that are actually often responsible for the scents that we smell. They're quite volatile. They kind of effervesce quite often. So this is wafting in the chemistry lab. These are often responsible for the scents that we smell, flowers, perfumes, anything. Anything you're smelling, 9 times out of 10 is going to be an aromatic hydrocarbon. And since they are often associated with scents and smell, hence the name aromatics, like things that smell good or have strong smells are considered to be aromatic. So we've called this entire category of molecules aromatic hydrocarbons. So I've got a bunch of them pictured up here on your screen. However, you can see that their main feature is that cyclic ring. So when you see those ring-like structures, you know you have an aromatic hydrocarbon. So let's talk a little bit more about this molecule I was talking about called benzene. I think it's a really, really cool molecule. So it's one of the most basic forms of an aromatic ring. It's going to be the one that we see the most. It can either have something substituted on it, just like here we've added some chlorines into our structure, or a bromine, or a carbon chain. So we can add different things into this benzene ring, or we could even attach a benzene ring to one of those really, really, really long carbon chains as well. So it's kind of cool that it's flexible in that manner, that it can kind of be the main part of the structure or even be a side feature as well. So one of the interesting things is that once we had this idea that we could have these cyclic structures, that we might be able to have something like benzene, when we were looking at it and we actually were able to start taking measurements of the bonds in the structure, what we noticed was that we could have the possibility of 2 structures, and those 2 structures did something very interesting. So if you look at my 2 pictures here, these are something called resonance structures. So resonance structures are structures basically where we could have 2 different equivalent structures. So if I went through and I was able to label all of these different hydrocarbons, all of these different carbons in the ring. Let's say it's 1, 2, 3, 4, 5, 6, okay? Arbitrary numbering, but we're calling this one 1, this one 2, this one 3, this one 4, this one 5, this one 6. Here you can see that between 1 and 2, you have a double bond. Over here, between 1 and 2, you have a single bond. So it kind of flips very quickly back and forth between these 2 structures. And so, one other key piece of information here that we haven't quite talked about yet is that single bonds are much longer than double bonds. When you have more electrons in between 2 different atoms, it can pull them much more tightly together. So single bonds are longer, double bonds are shorter, and triple bonds are going to be the shortest. So what we noticed when we had this resonance structure, basically that benzene was flipping back and forth between the 2 resonance structures so fast that they kind of took every benzene, those carbon-carbon bonds are actually halfway in between a single bond and a double bond in length, because it's basically like we could never tell which one was actually a single bond and which one was actually a double bond. It's relatively arbitrary. So I think that's really, really cool. So it's influenced a lot of the different representations of benzene that we have. So here we have the space-filling model where we can just see the carbons and hydrogens. However, again, we can't see the bonds that we have here for pretties. But when we're thinking about benzene, these are two of the most general representations we can see. Oftentimes in organic chemistry, we don't feel like drawing out all of the C's and all of the H's we could put into the structure. Again, chemists are lazy when we can communicate with each other in other ways. So basically, when you're looking at these two structures down here, what I think is really cool is this representation. Each point represents a carbon. Each line represents a bond between those carbons. And like two lines like this represents a double bond. So here, we have the same thing pictured here and here, exactly, just with a lot less kind of cluttering of information with all of those carbon C's and all of those hydrogens sticking off. So when we see something like this, it's called a line drawing, and so we just assume that anything that is not denoted is a hydrogen. So when I'm looking at this, I should have a carbon at this point. It has one bond, two bonds, three bonds, so I can assume it would form a fourth bond with a hydrogen. I just hid my hydrogens out of view because when we're looking at these intensely complex structures, things can get cluttered really, really fast if we're drawing the C's and the H's. So these are kind of two different representations we use that way, and what this one down here is representing is the fact that kind of like we don't know which bonds are single bonds and double bonds, and sometimes it doesn't matter to us in our chemistry what the single bonds and double bonds are. So we just put a circle in the middle to say, there are single bonds, double bonds somewhere. It's doing this resonance thing where it's flipping back and forth so fast that we can't specifically identify those bonds. These are some different representations of all of that same benzene molecule. So I think that's pretty sweet. So you also may have heard, maybe potentially, about benzene in another way that's not so exciting. So benzene in its pure form is also a known carcinogen. So it can cause cancer in humans and other, I'm assuming, mammals. So it's a known carcinogen for humans. And actually, oftentimes, compounds that can form benzene can be present in soft drinks, especially in energy drinks. They get loaded up with this for some reason. And so in certain temperatures or in certain amounts, in certain concentrations, as we figured out, they can actually react to form the benzene. And so a while ago, this article's from 2006, but I remembered reading it and I had to bring it back. But the FDA actually got on a lot of companies and said, you need to change your formulas because you're forming too much benzene in your soft drink from the compounds you're using. And like, it's not good for people. You need to stop. So we're actually concerned about consuming these compounds. We use them in certain ways, and when they're substituted into certain things, it's awesome. But like, for example, a compound that can form benzene is like sodium benzoate. It's used to preserve freshness. It's a preservative. So right here on my Mountain Dew bottle, I can find that. However, basically the FDA said you need to go back, you need to change your chemical composition of your pop, and you need to make sure you're not using too much of these compounds and you're not putting them with other compounds that are going to be able to make benzene because you're endangering people. And energy drinks are a huge culprit of this oftentimes. So stay away from those. There are plenty of other reasons to stay away from those as well, but stay away from the energy drinks. But the FDA did kind of do some sniffing around and kind of rooted out some of these problems. You can assume that what you're drinking is safe, but it's interesting that they kind of came back out with this benzene stuff and were like, hey, y'all need to shape up. Y'all ain't doing so hot. So maybe you've heard of benzene in that way before. So I think that's kind of interesting, kind of cool. So don't be drinking a ton of pop. Don't raise your benzene levels because you just drank and 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 all you drink is pop. Drink some water, guys. As long as you're drinking water, you should be fine. I'm also not a doctor. So let's get some practice talking about alkanes, alkynes, alkenes, and aromatic rings. So these are kind of some of the things I should expect you to be able to identify. So you should be able to look at the chemical formula and use those general chemical formulas to determine if this is an alkane, alkene, or alkyne, or to look at the structures as well. So here I have C10H22. Well, 22 is 2 times 10 plus 2, so I'd say that's an alkane. It fits that alkane format. If I'm looking at names like this, I have pentyne. I see that Y-N-E at the end. It's going to be an alkyne. Or if I look at a structure like this, I can see that I have an alkene because of the double bond in it. Here, obviously, it's a circle. It's aromatic. So that being said, go ahead and make sure you practice through these on your own. I've labeled all of them for you so you can practice. Right now, we're worried about just sorting them into categories and seeing if we can determine if something is an alkene, alkyne, or alkane. So that being said, that's Chapter 18, Part 1. See you in Part 2.